Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today session we like to do problem from handout number 6 regarding a topic that we are currently discussing, which is potentials. So that's what we're going to do. So shown here, I'm going to focus on question number 1 under the topic of potential difference. So this is what we are referring. So hope you have the handout with you, and then you can read yourself, try to understand it before seeing me how actually this problem can be solved. Okay, so let's do it now. So in this problem, it said here let E, and then we know E here is known as electric field intensity. And then from the equation given, we can see the E is in terms of Cartesian coordinate. So therefore, I suspect this problem should be solved using Cartesian coordinate. And then the question asks us to do what? To calculate VPQ, given P equal to minus 7 to 1 and Q equal to 4, 1, 2. So we're going to focus only on part 1 question. So therefore, this is what we're going to do. So let's redefine by taking the important component from the questions. So for this question of potentials, and then this is taken from handout number 6. Number 6. So given, so E in this question is given as minus 6 y over x squared in x directions plus 6 over x in y directions, finally plus 5z, and then you can see the unit of E is volt per meter. So please noted the unit now we're going to talk about when we solve problem. So make sure you look into the unit now as one indicator, important parameter when we solve problem. So the question wants us to do what here? Find VPQ. Okay, so we know from our discussion, V can have two meanings. V can be known as potential difference, or V can also be known as absolute potential. So we have to see the information given here. Since you are given 2 points to decide the potential, which are point P and point Q, therefore this V should have the name, should be known as potential difference. So that's what we're going to do. Okay, so what is potential difference? So from our lecture, from definitions, okay, we know that V, AB, I'm using definition. Remember our equation that derived together should be minus, because we know this equation must be based on the work done by external, negative, moving from where to where? From the reference B up to the destination A, and then E dot dl. So remember, this equation came from our definition that we discussed in our previous lecture. So I'm using it now. Okay, so I can see from these equations that it can be used. Why? Because I know the E and the DL can be defined based on our selection of coordinate. And from what we been informed, the E is based on Cartesian. Therefore, the DL also must be taken from Cartesian definitions, and we know based on Cartesian that the DL should be defined as dx in x direction plus dy in y direction plus dz in z direction. So remember, this is what we talked about in week number 1 when we solve handout number 2 together. Remember the table of handout number 2? So that come from that particular table. Okay, now let's solve the mathematics now. So the E is this E and the DL is this definition. So now we have to see in terms of mathematics now. Okay, in terms of mathematics, that VAB should be equal to, I'm going to put negative here, okay, just leave it as it is, and then I'm going to move from my point PQ, so therefore here should be Q, and here should be P, because now it should be PQ. So we're going to make it refer to our question, VPQ, so Q to P, and the point Q is given as 412, and the point P is given as -7, 2, and 1. Okay? And then when I do the mathematics, dot product, because this dot product now, the final solution should be scalar, no direction. So what's going to happen now? X dot x will give us 1, y dot y will give us 1, z dot z will give us 1. If x dot y will give us 0, x dot z will give us 0. So therefore, the common unit vector will only the one appear at the end of the solution. Should be what now? Negative 6y over x squared dx. That should be one solution, and then y and y should be plus 6 over x dy, and finally should be plus 5 dz. Okay? So now, let's solve the mathematics. So what I'm going to do now, okay, I'm going to left the negative. Okay, the negative now I'm going to, okay, let's put inside now should be the integrations of 6y over x squared dx minus 6 over x dy plus, minus 5 dz. Okay, moving from where to where? From Q to P. Okay, let's do the mathematics now. So I'm going to do, there are many ways of solving this mathematics. Remember, you can use the conversion. What we meant by conversion, we change everything in one variable. We have to do that. Why? Because one integration here, one variable. So therefore, we decide everything to be in x. So you have to change y into x, dy into x, dz into x. So that's one way of doing it. So I'm going to use a simpler way. So still applicable by looking at the mathematics per se, is but like this. I'm going to show you. Okay. So now I'm going to do the first part now. Do this part of the mathematics. I'm going to ignore the other first. I'm going to focus on this one. I'm going to ask myself, so this particular term only saying that the changing variable is x, because we are having dx here, so the only changing variable is x, and then we are saying other component which are y and z assumed to be constant. And where are we at this particular junction? We are at point Q. Okay, look at this mathematics, we are at point Q, and at this position my y value is equal to what? Yes, equal to 1. Okay, because I'm still at point Q. I haven't shift yet because I haven't integrate yet. I'm still original P. So I'm saying now I can replace now 6 remain as it is. Okay, and then I'm going to say the y can be substituted equal to 1. Okay, because this term saying to me that the only variable that need to be considered is x, therefore we can assume the other variable which are y and z assumed to be constant. And where are we at this particular junction? We at point Q, and look at point Q, the value of y is equal to 1. So therefore I'm going to say in this mathematics my y is equal to 1. Then I'm going to do my integration with respect to x. So the solution should be equal to 1 over x. Remember, that should be negative. And then I'm going to put the limit here from my 4 to minus 7. That's the integration. Okay? 4 to 7. Why negative? Remember, because x minus 1 here. I think you should know that. It should be negative 4 to 7. So that's done. That's we are saying now the x term have been completed. So now let's proceed now. So you can see after doing this term, the x variable have been shifted from 4 to minus 7. So let's do now. So I'm going to, so negative here, because negative, and then 6. But in this particular term, the variable now is y. So other than y, meaning that the variable x and z are assumed to be constant. And we can see this x here, correct? But now the x should taken which value? Should taken 4 or minus 7. Good. So the x must be substituted with minus 7. Why? Because after doing this term, we are saying x have been shifted from 4 to minus 7. Now we are going into this particular term. The x already shifted to minus 7, so we put minus 7 here. And then we know integrating of the y, we're going to give us y. And then we're going to put limit here, okay, from 1 to 2, because we're focusing on our y variable, 1 to 2. And finally, in this term, we don't see any x, we don't see any y, so we just leave it as it is, so 5. And then we know the integration of this, we're going to have z, and then the limit of substitution now from 2 to 1. Okay, so now when you solve this mathematics, okay, when you solve it, so what you're going to give us now? Okay, let's do the mathematics now. Okay, first negative and negative, so now it's going to become positive, so should be equal to what now? 6 over 7, correct? 6 over 7. Okay, and then minus becoming plus, because negative. 6 over 4, and then minus and minus becoming plus, plus 6 over 7, and then we know now 2 minus 1 is 1, okay, and then finally it's going to be, okay, 1 minus 2 should be minus 1, and 2 plus 5. Okay, when you do this, you're going to end this to become 8.21 volts, and then alhamdulillah is agree to what Hayat given us. so it's equal to 8.21 volt as well. Okay, so you can see now what I'm showing you something that yeah, method wise this can be depending on what method you want to use. So I'm using this method in my problem solving because for me it's much easier. But yet if you want to use a typical method by changing everything to X also can be done. So this is one way of solving it. So it's not a must, it's just a way. So alhamdulillah we have completed this problem. You can try doing other problem, for example part 2 and part 3 if you want to. So I'm just doing part 1 here just to show you how this can be done. But yet as you can see, whenever I solve I go back to the definition. So that's what make it look easy. So if you always go back to definition, the issue that we discussed in previous lecture, I think all the handout problem will become easy. Okay. So what I'm going to do now, I'm going to go to problem number 2. Okay. So in this problem, as you can see, we not given a field as starting point. Okay, what given here is a charge as our starting point. So now a point charge 6 nanocoulomb located at the origin in free space. So there's the word free space. Find Vp if point P is located at 0.2 and V equal to 0 at infinity. So let's focus on this problem now. V equal to 0 at infinity. Okay, what we have here, we have a point charge. Okay, let's make it simple by drawing diagrams. Okay, so this should be our X, our Y, and our Z. And then the point charge is located here. The value is Q. And the Q here is equal to 6 nanocoulomb. Okay, let's say it's a point at a certain position. Let's say we want to find the P located, let's say here. So what should be Vp? Okay, so the P as shown here, the position is 0.2 minus 0.4, 0.4. Okay, that should be the position of our potentials that we need to determine. Okay, so for number 1, it's clearly stated here, V equal to 0 at infinity. Okay, so therefore we can straight away say that we are dealing with absolute potentials. Okay, absolute potentials. So therefore we know that this problem is known as absolute potentials. And remember, when we talk about absolute potentials from previous discussions, okay, we know, remember VAB, remember the one that we defined the problem in the class, in the lecture, Q over 4 pi epsilon naught. Then we are saying 1 over RA minus 1 over RB. And then if this term is assumed at infinity, therefore what we are saying, the VA now is known as absolute potential given as Q divided with 4 pi epsilon naught RA. Okay, so that's the one we did together, because we know this is the thing that we obtain. So now, so what we have been asked here, position, so 1 point, and then we know that the reference is at infinity, so we can use this particular term to solve for this problem. So now what we're saying that Vp equal to 6 nanocoulomb divided with 4 pi epsilon naught. Now, the R here, I'm going to put Rp. Okay, what is Rp? Where our Rp is this distance, the distance from point P into the source. So that should be defined as our Rp. Okay, and then from vector that we learned, this should be equal to the value of 0.2 power of 2 plus minus 0.4 power of 2 plus 0.4 power of 2. So therefore, by substituting this value into this term, inshallah you can solve the problem. That should be a first part. Okay, so in this problem, I'm not using the E dot dl, I'm using the charge definitions, but I know that by assuming this infinity, the problem of VAB can be simplified to become absolute potential. So from the diagram extracting information, I put inside the general equation, and therefore you can obtain the solutions. That for problem part number 1. Okay, so that's done. Okay, let's do something that different here. So let's do for part number 3 now. Okay, shall we do that now? Part number 3. Okay, number 3. So the charge still at the origin, but now the reference is not 0 anymore. So now something that quite tricky. Now the potential reference is equal to 20, and it's not at infinity, it's at position nearby, so 0.51 and minus 1. So meaning that the reference is not infinity and the reference is not 0. So therefore we have to adjust our approach in solving this problem. Okay, so for number 3, so what I'm going to do here, okay, I'm going to alter a bit. I'm going to go back to the basic definitions of potentials. Okay, so now I'm using the definition of V. Instead of with limit, I'm going to say that it's equal to minus E dot dl. I'm not giving limits now. Okay, because just assume like that at this stage. I'm going to just make it without limit. So for point charge, source, okay, meaning that the E is equal to Q divided with 4 pi epsilon naught R square in all directions. Okay, that should be our definitions. And then therefore the mathematics now, therefore the V is equal to Q divided with 4 pi epsilon naught R plus constant. Okay, now because we don't want limit to be involved in this calculation, we just make it floating. So therefore the solution should become with a constant, because the integration is without any limit. So we know without limit we must add constant to the solution of integrations. Okay, now so what I'm going to do now, so since okay, I'm going to relate to the question now. So the question said what? Since V equal to 20, okay, V equal to 20 at what position here? at position minus 0.5, 1, minus 1. Okay, so therefore now we are putting position to our solution, general solution. So now, so remember this potential is true for a point charge. And then we know the point charge is located at origin. Okay, and then the reference given here 20 at this position. So what we can do now, we can use this particular equation to determine the constant, so that we are linking the general solution to take into consideration the reference of the problem now, which is 20 at this position. So now what we are saying, we are using this general equation now. So what we are saying now, 20, the potential now, 20 volt equal to what? Q still the same, 6 times 10 to minus 9. Okay, then we divide everything with 4 pi epsilon naught, and I'm going to put R here, plus C. Okay, and R, remember the R is the distance from the source to where the V is equal to 20. What is it? Yes, this. When the R now is equal to square root of minus 0.5 square plus 1 square plus minus 1 square. So what we going to have now, we're going to have the C. So therefore, the C going to be a number now, a solution, a numerical value. So now the C should be placed here. So by placing the C into this general equation, now we are saying this equation is referred to the reference of 20 volt located at this position. Okay, so now the C is the constant that linking the general solution that we used earlier to be considered. So whatever the solution that we're doing after this were based on this reference. Okay, so now let's proceed to our problem now. So therefore, okay, I'm going to go for now. So therefore VP, remember VP? VP, the potential that we want to find is equal to, I'm going to take this, Q, again, 6 times 10 to minus 9, because the point charge still at the origin, divide with the 4 pi epsilon naught, and RP, remember the RP we used earlier, the distance from our source to the point P, okay, which is minus 0.2 minus 0.4, 0.4, and remember to do what here? To add with the C. So therefore, you're going to get a numerical value. Okay, so this is a way that you can use. There are so many other ways that you can still use, but I'm just suggesting you the ways that you can use, because now the reference has been changed. It's not at the origin, not at the infinity, and furthermore the value is not 0. So therefore you have to make the definition of V to become floating, because we want to make it without any reference. So therefore you end with this term, and then you can say the C. So the C going to be the constant that linking you to the references that you are putting into your problem, and in this case the reference having the potential 20 and the position not at the infinity, whereby it's at this position. So therefore you can use that to determine the constant value and put back into the general equation. Therefore that equation now is becoming the equation referred to that given reference, and then it's repeating the same process as above. You're going to find the potential at point P now with the new reference then. Okay, so that should be how you tackle the problem. Okay, alhamdulillah, we done that. So shall we do one more problem? You think, or you think it's enough? You can do other problem yourself. Okay, you want to do one more problem. Okay, so let's do problems slightly different now. Not a point charge and not a given E. So let's say you have other structure in the problem. Okay, we're still referring to the same handout. Okay, we can see the problem here. Okay, so what given here is a line charge. How do I know line charge? Because I can see the unit here is nanocoulomb per meter. Okay, so each coordinate axis carry a uniform line charge of 20 nanocoulomb per meter in free space. So now still we are dealing with free space. Given point A 1, 2, 3, point B 6, 8, 10. Find VAB. So VAB, you can see now the 2 point of interest. Therefore, we're going to define this to be potential difference. Okay, not absolute potential, potential difference. So this number one solely to rho L. Okay, on the x-axis, that should be part 1, meaning that the potential difference due to one line charge along the x-axis. For part 2, the potential difference due to only one line charge along the y-axis. And part 3, solely to one line charge on the z-axis. And part 4, the potential due to all the 3 line charges. Okay, so let's do this. I'm going to do for number 3 first. Okay, just to show you the reason logic later on. Okay, so let's do this question, but we're going to focus on number 3 first. So let's do it now. Okay, I'm having a z-axis. So let's draw my z-axis. Okay. Point A, let's say, is located here. I'll just make it artificial now. Point A, let's say here. Okay. Point A, let's make it to be given as 1, 2, 3. Oh, nice number. And point B, let's make it here. So it's given as position 6, 8, 10. Okay, and then what given here? A line charge along the z-axis. So the line charge along the z-axis. So the line charge having density, I'm going to make it rho L, and we know that rho L here equal to 20 nanocoulomb per meter. Let's make it rho L generously. Okay, just write it to be 20 nanocoulomb per meter. So the question asks us to find what is the potential VAB. Okay, what should be our VAB? There you are. Okay, so which method that you want to use to solve problem? Should we use the electric field as the method, we define to be method number 1, or are we going to use the charge distribution as our method? We are calling that to be a method number 2. This is based on our diagram that we refer at the end of lecture, discussing about potential difference, and absolute potential. I believe should be lecture number 5. Yeah. So which method that we should use? Okay. So look at the question. I can see there's no indication about the dimension of our line charge, correct? Our line charge is only stated as having density rho L and residing along the z-axis for this particular part number 3. Does not mention anything about the length itself. So now, there's a chance for us to assume now. Because something not mentioned, we can use our assumptions, and the purpose of this assumption to make our problem solving simple. Okay, so now what I'm going to do, I'm going to assume, okay, just this is what I'm going to clearly state in my problem. I'm going to assume rho L is infinitely long. Remember? So when we said that rho L is infinitely long, so we have a special solution to it. And we know that from our previous, now you can see again, I'm using our experience now to solve this problem from our experience. So if you miss my lecture, if you don't do any revision, so now you lost. But now we are using experience, what we saw before. So now the E, and we call it rho L infinity. Remember that the one we did together in Coulomb's law. So it's equal to rho L over 2 pi epsilon naught R in R directions. Okay, so we have seen these solutions, and we know that this solution is referred to which coordinate? Yes, cylindrical coordinate. And then we use epsilon naught here. Why? Because the medium stated in this problem is free space. So therefore, this should be our standard solution. So knowing this to be the appropriate solution, so therefore to find VAB, I should use the first method, which is using the electric field. So now I'm going to say, now I'm going to use minus from where to where? From B to A, E dot dl as my approach. Okay, so you can see everything must have reason. You cannot simply say you want to use. So you have to have reason, because this reason is important so that you can explain to your fellow engineers later on why you choose that decision, so that they can agree or disagree. Okay, that's what reasoning is very important. So you cannot simply force people to agree with you, because that's what make our world become more complicated. All of us have our own reason, so make sure you justify your reason with academic background, not using other method. Okay, so let's do it now. Okay, so let's substitute now our VAB. Okay, now I'm going to call, so this should be equal to substitution now, minus, still there, okay, and then I can see E should be rho L divide 2 pi epsilon naught R in R directions, dot with, okay, based on cylindrical, the dl should be dr R direction plus R d phi direction plus dz z directions. Okay, that should be the dl based on our cylindrical coordinate. So when we do dot product, the R and R will give us 1, the R dot phi will give us 0, and R dot Z also will give us 0. So the final integration will only end with the R. So now, what is R? R is the radius. So what we're going to define now, the radius from the diagram is defined as a line joining our point of interest A to our line charge having angle 90 degrees. Okay, that's how we define this to be RA. And then if we do the same thing now, from line charge going to this position angle 90 degrees, that should be our radius B. Okay, so now what we have, we have this definition. So now, instead of general point B, I'm saying this should be represented by RB. Instead of general point A, I'm going to replace the general point A with the radius RA. So now I'm going to solve the mathematics where VAB equal to, okay, now should be rho L over 2 pi epsilon naught. Now I'm integrating the 1 over r dr should give me ln, and then should be RB over RA. So that should be my potential difference due to infinite line charge source. Okay, now so let's give it for our solution now. So finally, we're going to conclude for part 3 now. VAB part 3 equal to rho L here is 20 times 10 to minus 9 nano. And then our constant 2 pi epsilon naught. And then ln, I'm going to put general term first, RB over RA. So now, how we define RB now? So RB is taken from the diagram, okay? So we know that any point on this axis, the x always equal to 0, the y always equal to 0, but the only variable is z. So now to be at this position, the point here should be 0, 0, and 10. That should be the way you take that position. And for this point, so giving this here should be 0, 0, and what should be the z value here? 3. Okay, so from the diagram you can see, okay, where, okay, I'm going to write here where RA equal to 1. What should be the RA, the length of this particular structure? We know the point here 1, 2, 3, and the point here 0, 0, 3. Good. So it's equal to the square root of 1 square plus 2 square. Agreed? Okay, should be equal to square root of 1 plus 4? Yes, 5. Okay? And how about RB? RB equal to, okay, and then we know should be taken from this length, from our vector, we know that that should be defined as square root of 6 square plus 8 square. Okay, so 36 plus 64. Okay, you can get that. So that should be, and then you substitute everything, then you're going to get a value to it. That's how you define. Yeah? So I'm sure you can repeat the same method for the line charge due to the, the potential difference due to the line charge along the y-axis. Same repetition, you just repeat the same method I show you. And then you can do as well for the case potential difference due to the line charge along the y-axis. And for the final part, for number 4, what is said here, where due to all the sources, so what we can say, okay, should be V total should be equal to V case number 1, which is rho L along the x-axis, plus V rho L along the y-axis, plus V rho L z-axis. So this is what we call it to be V rho L due to the z-axis. So meaning that superposition, you can sum all the potentials due to the various sources. So therefore, that's what should be your final step. So I'm sure you can, inshallah, give a try. So I have shown you 3 methods to find potentials. So hope you will do more exercise because your quiz number 3 will be based on potentials. And then I'm hearing from the course coordinator, you're going to be test number 1 very soon. So we also need to prepare ourselves for test number 1. And test number 1 will carry quite significant marks. I think about maybe 15. So it's a lot. So make sure you give a try doing revisions. And then with that, I'd like to thank you for your attention. Inshallah, we're going to see each other. Assalamu alaikum wa rahmatullahi wa barakatuh.